Day at 8, 7 Central.
This is TV Ontario, Channel 19 in Toronto, Channel 59 in Chatham.
This is the first of 3 programs which deals with an area of geology not touched on in the Planet of Man programs: evolution and fossils, the history of life. Evolution is one of the great ideas of science, and it's also important to biology as well as geology. In fact, it illustrates very well how the 2 areas, biology and geology, come into contact. It's only through geology that one can really demonstrate evolution, demonstrated by studying the fossil record. The origin of life is another geological problem that's shared by biologists and also by chemists, by biochemists. In this hour, we shall look at the origin of life and evolution. Fossils, as well as being very useful for putting rocks in their correct position in the relative geological time scale, in other words, into a geological system like the Cambrian or whatever, also have a story of their own to tell. They have the story of the history of life to tell. And the very beginning of that story is obviously the origin of life. And if we're to look at the origin of life on the surface of the Earth, then clearly we have to look at the conditions on the surface of the Earth, at the state of the oceans and the state of the atmosphere at the time that life might have originated well back into the history of the Earth. Let's see what we can tell about the early atmosphere and the early oceans by looking at some very old rocks. There are 3 kinds of rocks that can tell us a great deal about the oceans and the atmosphere early in the history of the Earth. First, this banded iron formation, which in fact comes from Temagami, just north of North Bay. Then this uranium ore, which is from Elliott Lake and is essentially a sedimentary conglomerate. And then these red rocks. The one on the left is a very old red sandstone, and the one on the right is a piece of schist from the present day, which is weathered red in the present day atmosphere. Now, let's begin trying to draw conclusions by looking at the uranium ore from Elliott Lake. It consists of pebbles and sand. As I said, it's a conglomerate. But mixed in with that sand are some grains of pyrite and some grains of uraninite, and it's uraninite which is a uranium ore. But if we were to look at the sands and gravels of present-day streams, in other words, the modern equivalent of the sands and gravels which accumulated at Elliott Lake 2,300 million years ago, then we would never find pyrite and we would never find uraninite, because the oxygen dissolved in the stream water causes the uraninite and the pyrite to break down. So a conclusion we can draw from the Elliott Lake conglomerate is that at the time it accumulated, there was no oxygen dissolved in the streams which carried the sand and the gravel, and therefore there was no oxygen in the atmosphere at that time. What conclusions can we draw from this banded iron formation? Well, the bands consist of alternating rich and poor layers of iron oxide. The black layers are rich in iron oxide, the reddish layers are much poorer in iron oxide. This rock accumulated as a sediment in a sea. And in order to accumulate that iron oxide in the sea, it was necessary that there be periodically oxygen in the water to produce the black oxygen-rich bands. So there are two conclusions we can draw from these two rocks. One 2.3 billion years old, the other one just a little bit older. Now then, what were the gases if they weren't oxygen in that atmosphere? Well, they may have come from original gases that were retained by the Earth from the time that it accreted from particles of dust and gas at the time of the origin of the solar system. We think that's unlikely because one of those gases would be neon, and we have at the present day only 100 billionth of the neon that we ought to have if those early gases were retained. The other source that those gases may have come from is a volcanic source. Look at this example of basalt lava. In it are many gas bubbles. The gases emitted during a volcanic eruption are very hot and acrid, at perhaps 1,000 degrees centigrade, and special piping has to be used to lead the gases away from the vent because of their heat and the acidity. The gas can be collected in quite ordinary glass flasks, which are then taken back to the laboratory for analysis. Volcanoes, of course, are quite unpredictable, and a quick retreat is very often a wise move. Surprisingly enough, over 3/4 of the gas emitted is usually water, with a substantial content of carbon dioxide and sulfur dioxide as well, and then some nitrogen and hydrogen, sulfur and chlorine. If you think that's dangerous and foolhardy, I wonder what you'd think of two Russians who sailed down a lava flow on a raft of basalt in 1938 in order to collect volcanic gases. If the atmosphere then was composed of gases erupted from volcanoes and contained no oxygen, then we're left with a problem. We're left with the problem of where did the oxygen come from, which was available in the water at the time that the iron formation was deposited. Well, the answer to that problem probably lies in fossils such as this. You see these layers here, rather dark compared with the intervening light layers. Well, the dark layers are layers of algae. They were once a rubbery sort of scum, and the light layers between the dark ones are layers of mud that was washed onto the top of that rubbery algal layer. So it's in algae that existed at the same time as the iron formation was deposited, not as complex algae as the one you see here, but simple relatives of this one, that we look for the source of the oxygen. One of the places where algae are most in evidence is on the seashore. The seaweeds, the brown and the red and the green seaweeds of side and water. They have humbler relatives which one can isolate in a drop of any dirty water from a pond. These humbler relatives also function in much the same way. They use sunlight, and they have chlorophyll in them, and they use carbon dioxide and water. This single-celled algae lives and dies and reproduces within a single-cell wall. They're very beautiful, and there are many, many thousands of varieties of such single-celled algae in both the oceans and in fresh water. This one is much thinner than a human hair. Here the chlorophyll, which uses the sunlight in the life process of the algae, is present as dark patches within the cell. And here the protoplasm within the cell wall is circulating, but once again only a single cell. Beneath the surface of ponds and also in the oceans of the world is where the algae live and where their waste product is produced. That waste product, so very important to us, is oxygen. Algae like this, branching thinner than a human hair, producing the oxygen we'll eventually breathe. Those little single-celled green algae are responsible for about 50% of the oxygen of the present atmosphere. The oxygen that we breathe and that every complex animal uses for its life processes. There are very many kinds of algae at the present day, and they're also widely represented in the fossil record. One of the places where they're best exposed to view is on the shores of one of the islands in Great Slave Lake. This is a veritable algal meadow preserved in rock. The algae thrived about 1,700 million years ago and were covered by a few feet of Precambrian sea. The sea bottom was mushy and muddy. Several thousand feet of rock have since been removed in order to give this exhumed sea bottom. Now, picture the situation. Algae, particularly little single-celled kind, are producing oxygen in the water. That oxygen is combining with iron in order to produce iron formation. Now, there's only so much iron in the seawater. The iron has to come from the land originally, dissolved in water of rivers, but there's only so much of it. And what's going to happen when it's all used up? Well, the oxygen, instead of combining with iron in the water, is going to bubble through to the surface and start producing an oxygen atmosphere. Well, that's what we would assume would happen. How can we see this in the geological record? Well, one of the things that happens is that about 1.8 billion years ago, we find that iron formation disappears. There are no banded iron formations of the kind that there are at Temagami younger than 1.8 billion years. So conditions obviously changed. There are no more uranium deposits of the kind that there are at Elliott Lake after 1.8 billion years ago. Instead of those deposits, which depended upon the early atmospheric and ocean conditions, we find red beds. Beds of sandstone that are red-colored because they contain iron oxide, and that iron oxide is derived from the action of oxygen in the atmosphere on iron minerals in rocks on the land surface. This is still going on at the present day, and that large sample is a sample of schist, the iron minerals of which have been oxidized by the oxygen in the present atmosphere. So that, if you like, was the watershed in the history of the atmosphere 1.8 billion years ago. Let's just look at that in summary. The accumulation of the Earth by cold accretion, particles and gas about 4.6 billion years ago. We think it's probable, but not certain, some scientists still think it's possible, that the early gases escaped. We think they escaped. Life originated perhaps 3.6 billion years ago or so, and in the oceans of 3.3 billion years ago, algae were evidently present to produce oxygen, which led to the deposition of banded iron formations. About 1.8 billion years ago, the iron in the seas was used up, and it bubbled through to the atmosphere, where red beds were then produced by atmospheric oxygen acting on the rocks on land. There's a second, probably important level, about 0.6 billion years ago at the beginning of the Paleozoic, when there was a lot of oxygen in the atmosphere and complex life began to evolve. We'll look at that in a later program. So much for the atmosphere and the oceans, but what were the ingredients for life and how did life begin? One of the first experiments carried out in order to test hypotheses on the origin of life was conducted by Stanley Miller in 1953. In a flask, Miller mixed the suggested ingredients of the early atmosphere: methane, ammonia, water, and hydrogen. And then through this gassy, watery mixture, he discharged an electric spark. And when the products of the experiments were carefully analyzed, new material was found to have been created. In fact, 4 amino acids were found, the structural units of proteins which make up all living matter. Much more complex apparatus is now used to provide more careful chemical conditions for experiments such as that carried out by Miller. In this case, the water vapor is being frozen out in order to get exact proportions of methane and ammonia. And instead of the electric spark, which Miller used, ionizing radiation, intense radiation, is now used for about an hour. The use of this radiation is obviously not without its hazards. Although no visible change can be seen in the mixture, new molecules are being synthesized. The solution, when analyzed very carefully in sophisticated apparatus, shows that sugars and purines and pyrimidines, which are all essential elements of living matter, have been formed. All these molecules are necessary for the evolution of life. The mixture of gases which Miller used, ammonia and methane dissolved in water, is not a mixture that most scientists would start with at present. That was in 1953, and since then most people have begun to think that probably those gases, as I mentioned, were lost from the early Earth, although they are present in the atmospheres of other of our planets. Most scientists would now start with water, carbon dioxide, nitrogen, hydrogen, some carbon monoxide, which is another of the volcanic gases, and they would use an energy source probably similar to Miller's, a discharge simulating a lightning stroke, or they might use heat, or they might use ultraviolet radiation, or even shock from a meteorite impact has been suggested as a possible energy source to make more complex molecules out of those gases in a watery medium. And water is very important. We're very fortunate on this planet to be just the right distance from the sun. We're not too far away so that the water doesn't freeze, and not so close like Venus is that the water is lost because it's too hot. So in the watery medium, with the application of energy, one can make other molecules from the gases produced by volcanoes. One of those that one can make is cyanide. Now that seems to be a very, very strange starting point for life. Anything like you or I would die very quickly given a dose of cyanide, but it was probably one of the compounds that was present in the waters on the early Earth. And don't think of those as oceans. Think of them as isolated pools or lakes or small seas or whatever, with hydrogen cyanide in. Another of the molecules one can make with those volcanic gases is formaldehyde, which some of you probably know. So that's the first step, making slightly more complex molecules like formaldehyde, hydrogen cyanide, with a discharge or a shock or whatever. Life, however, doesn't consist of hydrogen cyanide and formaldehyde. It consists of very complex molecules, amino acids, which go together to form proteins, and also nucleic acids. Some of you may have heard of RNA and DNA. These are the two nucleic acids which are present in all life except viruses, which may not in fact be living at all, and some bacteria-like objects. In order to get these from things like hydrogen cyanide and formaldehyde and whatnot is a bit of a problem. From hydrogen cyanide, one can produce one of the ingredients that go to make nucleic acids without too much difficulty. It's been done in a laboratory. One can make some sugars from formaldehyde and calcium carbonate. But it's very difficult to know exactly what the next step was. But what we can think of is of those seas turning into a kind of organic soup with some amino acids in them and some proteins and maybe in some places some nucleic acids. And if you get a soup of that kind, and think of it as a kind of a very thin chicken bouillon, droplets will sometimes form naturally. A wind blowing over a scummy surface will produce droplets. In some rather thick liquids, droplets form naturally. And one can also produce droplets if you dry out, for example, a liquid that's got amino acids in it, and then add hot water. What you get afterwards are droplets. Or maybe on the flanks of a volcano, a water rich in amino acids dried out, and then when some hot water was added, one got little droplets. Now, the importance of those droplets is that they isolated sort of chemical reaction tanks, if you like, little capsules of mixtures of amino acids, proteins, nucleic acids. And they together, in some place, one of the many, 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 many billions of droplets, in some place may have formed a critical mixture which divided and took the step, if you like, to life. It would be a very critical mixture. It would be a very peculiar place, because although ultraviolet radiation is a good starting point as a means of making molecules, organic molecules, it's lethal to complex molecules. It's lethal to our molecules. If the ozone layer, which protects us, the oxygen-produced layer in our upper atmosphere, were suddenly to disappear, then we'd be frizzled in an instant, because ultraviolet radiation is lethal to our cells. It would be also lethal to the complex organisms in this critical mixture if there was too much of it. So we must imagine somewhere in that soup, complex molecules forming in a critical mixture, in a little reaction tank droplet, being protected from further ultraviolet radiation, maybe in a cave or somewhere like that. But that's how life probably started. The attributes which must have been possessed by that first living organism would be first the ability to grow, growth. They could grow by absorbing molecules from the organic soup. Much more important was what happened during division. If division is random, as it would be in just an ordinary droplet, without a critical combination of proteins and nucleic acids, then the droplet can't be said to be alive. But once there was some control over the products of the division, that control being exercised by a nucleic acid, then the organism, the droplet, or the cell, however you care to describe it, could be said to be living. In other words, there was the beginning of the inheritance of characteristics. A droplet just wouldn't divide into two pieces. It would divide into two more or less replicated pieces of itself. And that was the step which marks what we could call life, the transmission of information from one generation to the next, inheritance. Now, the exact transmission of information, as exact as it is in ourselves and advanced organisms, had to wait until there were good packages of nucleic acids, chromosomes. And that kind of thing, in other words, growth, division, and duplication of the organism by well-organized nucleic acids had to wait to another stage. Now, we can check out that more or less hypothetical sequence of steps. We can check some of the steps in the laboratory, but we can fully check out those steps if we go back to the rock record again. The rock record is not very rich in fossils, but there are some around, such as these in the Gunflint Chert from Lake Superior, which enable us to see what sort of organisms existed. For example, these from 2 billion years ago. They just looks like a mess, but in fact in there are cells rather like this, obviously in the process of division. This might be one of the first cells which divide. Now, another thing that we can do is we can go to look at the very simplest of organisms that still exist at the present day and assume, and this is a big assumption, that some of them are like those very early organisms. So let's look at algae again, and this time let's remember that maybe the distinction we make between animals and plants was not as clear-cut then as we think that it is now. To the casual observer, but much closer observation reveals that slime to be a multitude of green plants, algae. But not all algae are the filamentous kind. Here, evolution has produced an organism that's much more animal-like than plant-like. This one, for example, has still got chlorophyll, which shows us the dark spots within the body wall, but the body wall is flexible, and it moves around rather like an animal. It absorbs sunlight, and it gets its energy just the same way as a plant does. But it's driven along by little flagellae that are marked by the arrows here, but are almost invisible, little whip-like flagellae. And this one has an eye spot, which guides it to areas where sunlight is strong. In this relative, the flagella is much more obvious and clearly drives the organism along. And this one has no chlorophyll. Here, reproduction of typical algae is shown. The cell simply divides into two. You shouldn't think of those algae as relics of organisms of 2 or 3 billion years ago, but they do tell us some interesting things about what very primitive algae can do and what they can't do. One of the interesting things is that the pigment, the light-sensitive pigment in the eye spot of one of those little algae is the same pigment as in the retina of the human eye, which tells us something about once a good compound is discovered, it can be carried on for a long time into very different organisms. Another thing that we saw there was the development of sex. Now, sex provides many advantages to an organism. It allows for variability. That is, with two parents, the offspring will be different from each of the parents, perhaps a little better adapted, perhaps a little less well adapted, but variable and given the opportunity for better adapted forms to be selected and to be the progenitors of future generations. We also saw the beginnings of colonial organisms, not just one cell, but many cells. These are all things then that we've seen in very, very simple algae. The kind of organisms, not the same organisms, but the kind of organisms that were probably around in the very early days of living organisms on the Earth. Now, how we get from those very simple organisms, whether you call them animals or plants, to the complex organisms that we find in the 600 million years of the relatively rich fossil record, is a big, big question mark. We really have very, very few ideas about how to fill in that gap from the very simple organisms to the very complex ones. But we do know that natural selection had begun to operate, and we owe our understanding of the rules of natural selection to Charles Darwin. He developed the idea in the middle of the last century, and it's not very long since the furor over his theory of evolution by natural selection died away. Darwin's proposal that apes were the ancestors of man was probably one of the most controversial ideas of the 19th century. But Darwin's subjects were not always as obviously interesting as apes. Barnacles, for example, occupied him for nearly 7 years. Barnacles of the local seashore in Kent. And eventually he wrote a highly illustrated monograph on barnacles. Much of his work was done in his home in Kent in southern England. He was lucky enough to inherit a fortune and was able to work at home in his own study and small laboratory. The conditions at home were very much more comfortable than those that he experienced when he was young, in his 20s, between 22 and 29, when he spent 6 years on the Beagle, a British Navy ship that went on a voyage around the world, and Darwin was the naturalist. The climax of that voyage for Darwin was the Galapagos Archipelago. The islands of the Galapagos Archipelago are rather like those of Hawaii. They're volcanic islands formed of basalt, and there are 14 of them in a group, quite isolated from one another by cool, deep water of the Pacific. They cover, in fact, about 23,000 square miles of Pacific Ocean. The conditions on the island differ, rather, from one island to another. The climate differs and the vegetation differs. Some are dry and some are much wetter. But on the coasts, the sea lion is a ubiquitous animal. It's the same kind of sea lion as found in South America. It's a strong swimmer and probably colonized the islands soon after their origin as volcanoes that peaked above the sea. The sea lions are still quite friendly, despite the fact that many of their ancestors were killed off by sealers and by Navy ships that visited the island in the 18th and 19th century. But the interest of Galapagos to present-day scientists, and also to Darwin, are not the sea lions, which are just the same as those on other coasts, but in the animals and in the plants, which are different from the mainland. This albatross, for example, is only found in the Galapagos Islands. This is part of its rather unusual courtship dance. As well as the birds, the reptiles are very interesting. They differ from island to island. These are small lava lizards. They differ in their color and in their size and also in their behavior from island to island. They probably arrived on rafts from the mainland, where their ancestor is now extinct. There are also much larger lizards. This one's about 4 feet long. It too is different from lizards on the mainland, although large lizards are quite common. But seagoing lizards are very unusual. In fact, this one on Galapagos is unique. The tortoises are also very interesting and again differ from island to island. Darwin noticed that the tortoise on Santa Cruz Island has a very large, round, domed shell and likes loafing around in the water, whereas the tortoise on Albemarle Island has long legs and a long neck, which is very good for wandering over blocks of lava. The tortoise on Duncan Island has a different shell again, turned up in front and down at the back. This probably has something to do with the hot, scrubby vegetation of Duncan Island. It probably keeps the tortoise cool. Darwin and subsequent scientists, however, are very interested also in the finches of the Galapagos Islands. There are 13 species on the islands and another one on the Cocos Islands to the north. Their bills were interest to Darwin, a big bill for cracking big nuts, a medium one for medium seeds and nuts, and this one not very good for nuts or seeds at all, but very good for poking into cactus flowers. The different kinds of finches have different ways of life adjusted to the conditions on the different islands. Darwin surmised that the reptiles, the tortoises and the lizards, must have arrived on the islands on natural rafts, on logs or trees, which had floated out from the South American coast, brought by ocean currents. He surmised that the finches must have flown there, obviously, although they're very poor flyers, and probably not very many of them arrived on the islands. And this all happened at least 1 million years ago, when the islands first appeared above the surface as volcanoes or volcanic vents. Now, it was what happened after the lizards and the finches had arrived which was the key to Darwin's subsequent understanding of natural selection and evolution. The finches and the reptiles spread pretty quickly to the other islands, and on each of the islands the conditions were different. In particular, for the finches, the food was different. On some of the islands, the main food was large seeds. On other of the islands, the main food was small seeds. On other islands, the main food was insects which were lodged in the crevices of cactus plants, and so on. Now, in order to survive, the finches which lived on an island with a particular kind of food supply had to be able to get at that food supply. And if you're a finch with a big, thick bill, then it's not much good for getting at insects that are in the crevices of cactuses. And therefore, the offspring, which, remember, are all a little bit different from their parents, which were best able to deal with the gaining of the food supply, in other words, the offspring with the slightly less thick bill, would be the ones that would survive and go on to breed and be the progenitors of future generations. Now, we can see the result of that diagrammatically with just a few of the finches, just 5 instead of the 13 that are present on the islands. This finch has presumably become adapted to eating insects or perhaps at poking into crevices and cactuses, whereas these are very evidently finches which have become adapted to cracking seeds or perhaps nuts. And Darwin surmised that that must have taken place very gradually as each succeeding generation was better able to do the job. And, of course, the same applied to the tortoises. The tortoises which survived on the island with the large blocks of lava as the surface would be those that were best able to move across the surface. And that would be the ones with the slightly longer legs. And gradually, then, different kinds of tortoises and different kinds of finches and different kinds of lizards developed on the different islands. Now, that was controversial enough in the middle of the 19th century, but Darwin went on after writing The Origin of Species to write The Descent of Man and to expand his ideas to man and his ancestors. And in the concluding sentence of The Descent of Man, Darwin wrote, "Man still bears in his bodily frame the indelible stamp of his lowly origin." And one only has to look at a gorilla skull in order to see the kind of comparison which led Darwin to write that sentence. Now, controversy raged for many years after Darwin wrote that, and in some areas the teaching of evolution was declared a crime. And those who went ahead anyway were sometimes charged and brought to trial. One of the most famous trials took place in Tennessee in 1925. Dr. Mather was one of the participants in that historic affair that became known as the monkey trial.
The law was passed by the legislature of Tennessee on March 13, 1925. It made it a crime for any teacher in the public schools of Tennessee to teach any theory that denies the story of the divine creation of man as taught in the Bible, and to teach instead that man had descended from a lower order of animals. Somehow, many of the men of religion in those days felt that such an origin for man was destructive of the religious beliefs that were so vital in the life of many people throughout the country. Anyway, they passed the law. And immediately, the American Civil Liberties Union in New York City announced that if any teacher was arrested in Tennessee for violating that statute, the Civil Liberties Union would come to the defense of that teacher because, in the eyes of the lawyers associated with the ACLU, the Civil Liberties Union, such a restriction upon teaching in schools and colleges was a very serious violation of the freedoms that are guaranteed to all American citizens by our Constitution. So the Civil Liberties Union announced, and it was publicly spread throughout the papers, that if any teacher in Tennessee was arrested, the Civil Liberties Union would come to the defense. Well, shortly thereafter, some men in Dayton, Tennessee, got the idea that it would be a very fine thing for Dayton, a little sleepy town in the hills of the southern Appalachian area. It'd be a fine idea to have such a trial held in Dayton. It would put Dayton on the map, as George Rapelier said to the chairman of the school committee. Anyway, within a very few days, George Rapelier and Doc Robinson persuaded a young school teacher, John Scopes, to stand trial for a violation of that statute. John was a little bit reluctant, but when he was assured that all expenses would be paid and no serious consequences would ensue, he said yes. And so he was indicted for violating that statute. This, of course, was broadcast throughout the papers quite generally. Down in Florida, Mr. William Jennings Bryan is still remembered as one of the great silver-tongued orators of his day. I remember I heard him speak myself when I was a student in Denison University in Granville, Ohio. Some of us young fellows from Denison walked 7 miles over to Newark, Ohio, to attend a political rally at which William Jennings Bryan was the speaker. He was candidate for the presidency of the United States at that time. He was a magnificent figure of a man and had spellbinding characteristics so that he could take an audience and wrap it up and do whatever he wanted to do with it. Down in Florida, William Jennings Bryan saw the papers that John Scopes was going to be tried in Dayton, Tennessee. And so Mr. Bryan immediately announced that he would go to Dayton, Tennessee to assist in the prosecution of this young, well, I think he characterized him as an atheist, an infidel, or an agnostic, or something of that sort. And of course, what he was doing was undermining the morals of all of the boys and girls in the Dayton High School. Publicity was given to that announcement. Up in Chicago, Mr. Clarence Darrow read the papers, and he saw that Mr. Bryan was going to go to Dayton. Mr. Darrow had been a supporter of Mr. Bryan in his first campaign for the presidency of the United States way back when. But Clarence Darrow thought that Mr. Bryan's religious ideas were absolutely idiotic, and he welcomed the opportunity to cross swords with Mr. Bryan on religious affairs. Well, the thought struck me there in Cambridge, Massachusetts, that somebody ought to be in Dayton to defend a religion that would be respectable in the light of modern science. And I thought I knew what that religion was. So as it worked out, in accordance with Roger Baldwin's instructions, I arrived in Dayton, Tennessee on a Friday afternoon. The trial had been in session just about 1 week. When I got there, I was met with a very serious surprise. That very morning, Judge Ralston, who was the judge in charge of the whole trial, had ruled that inasmuch as the defense had really admitted that John Scopes had been teaching that man was descended from a lower order of animal life, it was unnecessary for anybody to testify concerning the relations between the theory of evolution and the stories of divine creation as told in the Bible. Therefore, the expert witnesses, so-called, the expert witnesses that had been assembled to testify concerning that aspect of the statute were not going to take the witness stand. Therefore, immediately after I got to Dayton, they put me down in front of a typewriter on a little table and told me to write out a statement of what I would have testified had I been permitted to take the witness stand. There were 3 objectives that we had. Surprisingly to most people, the first objective was to be sure that John Scopes was convicted. We weren't there to get him acquitted. Be sure that he was convicted under circumstances which would make possible the appeal of the judgment on the basis of the constitutionality of the law. We wouldn't have been at all disappointed had that appeal gone through the Supreme Court of Tennessee up to the Supreme Court of the United States. And that was one of our objectives, to get a conviction that could be appealed with the loopholes in the conviction so that the appeal could be based primarily on the constitutionality of this law, which all of us were firmly convinced was a violation of our Constitution. Our second objective was to present to the court and through the mass media to the world at large the facts on which the doctrine of evolution is based, and explain why that doctrine is so important in almost every field of science. The third objective was to present our argument that the theory of evolution was not necessarily destructive of the fine moral and ethical principles that are embedded in the creation stories in the Bible. Well, I was to write a statement, which I did, and by Saturday evening late, I'd finished it, and then the mimeograph machines took over, and Monday morning, July 20, 1925, the press wires were busy transmitting excerpts or summaries of those statements. There were nearly a dozen of them altogether. And that material was published in the newspapers clear around the world. Monday morning, after the statements had been admitted for the record, the Judge Rawson turned to the defense lawyers and said, "Have you any other witnesses you want to call?" And Mr. Darrow stood up, and in his inimitable fashion, he said, "Yes, Your Honor, we would like to call to the witness stand a man who is undoubtedly one of the nation's greatest experts on the Bible and the relation of the Bible to modern science. He's been speaking about it across the nation. He has talked to Chautauqua audiences and so on and so on and so on." But he said, "We're not quite sure that he'd be willing to come before us here on the witness stand. Maybe he wouldn't want to let us ask him questions." The man we are referring to, of course, is Mr. William Jennings Bryan. Bang over the audience, of course. And Mr. Bryan jumped right to his feet and said, "Of course I'll take the witness stand. No atheist, agnostic, or infidel can ever say that William Jennings Bryan was afraid to face the questions that might be asked." And his associates there at the prosecution lawyer's table did their best to get him down and not let him come, but he insisted. So that afternoon, Mr. Bryan took the witness stand, and Mr. Darrow questioned him. Well, I mustn't take much time here, but among the questions, of course, was the one about the days of creation week. Were those days of 24 hours like our days today, or what were they? And Mr. Bryan responded to that question, "Mr. Darrow, if you knew your Bible the way I know mine, you would know that over in the book of Psalms it says that a day in the sight of the Lord is as 1,000 years, and 1,000 years is a day." Darrow zeroed right in on that opening that Bryan had given him, and he said to Bryan, "Well, now, if a day could have been many hundreds of thousands of years, as you suggest, couldn't a day have been a geological period or a geological era?" And Bryan really made no intelligible answer, just a grunt to that. Well, Darrow led him on through many questions, including, of course, the expected question about Jonah and the whale. And Bryan correctly said it wasn't a whale, it was a big fish. But eventually, they reached what I considered the climax of that confrontation. Darrow referred again to the Garden of Eden story and asked Bryan if he believed that the serpent was condemned to crawl on the ground after he had tempted Eve. And Darrow replied, "Of course I do." "Well," said Mr. Darrow, "how do you suppose the serpent got around before it was condemned to crawl on the ground?" "Well, I hadn't thought about that." "Well, do you suppose it had legs and could have been walking rather than crawling on its belly?" "Well, maybe so." "Ah, then that would be a sort of a process of evolution, wouldn't it, Mr. Bryan?" Whereupon the judge slammed his gavel, adjourned court, and that confrontation ended. When court resumed the next morning, nobody and I mean nobody, had any reference whatsoever to the fact that when court had been adjourned, a witness was in the witness chair and presumably should be there when court was resumed. But that part of it was put completely out of any attention whatsoever. The last bits of legal maneuvering were completed that Tuesday morning, and then the judge turned to the lawyers at the table for the defense and asked if they had any remarks they would like to make to the jury. Mr. Darrow stood up and in his inimitable fashion, hooking his thumbs into the galluses, nobody had coats on then, it was July in Tennessee, and addressed the jury. Gentlemen of the jury, you understand, I'm sure, that we came here to test the constitutionality of a law which we believe violates both the letter and the spirit of the Constitution of the United States. Now, we cannot test that constitutionality unless our client is found guilty, so that we can appeal to a higher court and eventually to the Supreme Court of the United States. I'm sure you understand that. So don't think it would be conferring a favor upon any member of the defense if you should fail to find the defendant guilty. Not very often does a lawyer ask the jury to convict his client, but Darrow had heard rumors about some of the members of the jury raising questions concerning the iniquity with which John Scopes had been charged. And he wanted to make sure that the first objective of the defense, to test the constitutionality of the law, was made possible by the court there in Dayton. The prosecution lawyers waived their right to address the jury, and so the Judge Ralston, charged the jury. And in his charge, he said, now, gentlemen, if you should find the defendant guilty, of course, everybody in that crowded courtroom had the thought, of course they will, if you should find the defendant guilty and are content to have the minimum fine of $100 assessed as the penalty, just bring in the verdict of guilty and I'll assess the fine. Whereupon Tom Stewart, a brilliant young man who was among the lawyers of the prosecution group and who was the Attorney General for that district of the state of Tennessee, leaped to his feet and said, I beg your pardon, Your Honor, but I had thought that the jury would assess the fine rather than the court. Oh, no, said Judge Ralston. This is just like my bootlegging cases. I've had scores of them. I always assess a fine of $100, and this is a good deal like that. And while he was rambling on, Mr. Stewart buttoned up his lips and sat down. Now that was one of the most dramatic moments in the entire trial, although not a single one of us was aware of that fact. When the case was carried to the state Supreme Court, that court ruled that inasmuch as the judge was in error in having assessed a fine greater than $50 without having the approval of the jury, the entire proceedings were null and void. The case was remanded back to the circuit court with the footnote that the Supreme Court of Tennessee could see no useful purpose in having John Scopes tried again.
A very interesting story, I think you'll agree, and it's also interesting to remember that it was only in 1969 that that law in Tennessee was removed from the law books. There's not much need now for missing links. Over the last 40, 50 years, many skulls have been found which make man's own ancestry pretty clear, as we can see if we look at this row of diagrams. This is the top half of a gorilla skull with a protruding jaw, very large canines, and a heavy brow ridge for the anchoring of neck muscles. There's the brow ridge. Now, gorillas are often a line of their own. They're not man's direct ancestors, but this one is from about 1 million years ago. still a protruding jaw, heavy eyebrows, like the common ancestor of gorillas and man might have been. And here, a Pithecanthropus from about 600,000 years ago, still quite a brow ridge, protruding jaw, and quite a strong canine. And here, Neanderthal man, which had in fact a larger brain than present man in many cases. The average size was quite significantly larger than our own. Still quite a heavy brow ridge. Neanderthal man became extinct, and it was from a relative of the Neanderthals, this one here, from about 100,000 years ago, that we ourselves, with our very large brains and poorly developed brow ridges, developed. Now, we have to remember that man has put all his evolutionary eggs in practically one basket, into the large size and the organization of his brain. And we must remember that this is only one of our capabilities, and it's the one that gives us ascendancy. And like other animals, it may only be a temporary ascendancy. Neanderthal man became extinct 40,000 years ago. Other creatures with one particularly well-developed characteristic have also become extinct. We must remember that we also may have the same fate. Let's look back and put ourselves, our own species, in perspective. The key event which led to the development of all complex life on Earth was the release of oxygen by algae. The oxygen itself and the ozone produced from it are both vital to the survival of all complex organisms. The primordial organic soup in which life itself originated can never again exist on Earth. Organisms themselves have irreversibly changed the chemistry of the atmosphere and the oceans. The life of the Paleozoic sea floor was a result of 2.5 billion years of mutation and natural selection. In that perspective, the evolution in the last 500 million years, and particularly our own, has been quite explosive.